So we now want to look at the grand canonical formalism, and this turns out slightly easier to handle. Of course, in the grand canonical formalism, we know that the particle number is varying, and if nk denotes the occupation number of the kth level, then I know that sum over k nk must be equal to the total particle number, and the energy is given by epsilon k nk sum over k. So that the grand canonical partition function q, now eta denotes both for fermionic as well as bosonic systems, is given by n e to the power beta mu n. So the prime that you see over the sum essentially denotes a restricted sum. You will see now while y is that is minus beta e, which is going to be, if I replace the e from here, is going to be sum over k epsilon k nk. Now the restricted sum essentially means that one has to ensure that this occupation number, once you're summing over all possibilities, but one also has to ensure that these possibilities must also sum over to n, the total particle number. So therefore it's a restricted sum over this occupation numbers. One can convert this restricted sum into an unrestricted sum by introducing a delta function and writing down this as k epsilon k nk. Now we carry out the sum over n first and take care of this delta function and replace the n by sum over nk, so that I have sum over nk, the unrestricted sum, e to the power beta sum over k epsilon k minus mu nk. This sum over k becomes a product because it's in the exponential, and we take it out and rewrite our partition function in this way: beta epsilon k minus mu nk. For a fermionic system, let's say we write qf. Now nk can be either 0 or 1. So essentially then you have product over k 1 plus e to the power minus beta epsilon k minus mu. For a bosonic system, nk can be anything. For a bosonic system, this sum e to the power minus beta epsilon k minus mu nk is equal to 1 plus e to the power minus beta epsilon k minus mu plus e to the power minus 2 beta epsilon k minus mu, so on and so forth. And this is nothing but a geometric series which you can sum as 1 minus beta epsilon k minus mu, right? So that the product, the partition function for the bosonic case becomes 1 minus e to the power minus beta epsilon k minus mu. Fortunately, we don't have to deal with q, but we have to deal with ln q. And there the advantage is, if I take ln of qf, you will see that this quantity is nothing but sum over k ln 1 plus e to the power minus beta epsilon k minus mu, and the bosonic partition function is sum over k minus ln 1 minus e to the power minus beta epsilon k minus mu. Both of these I can combine and write down q eta, not q eta, but rather ln of q eta is minus sum over k ln 1 minus eta e to the power minus beta epsilon k minus mu. But I also note that there has to be a eta outside, so that for a bosonic case when eta is plus 1 I get this answer, and for a fermionic case when eta is minus 1 I get this answer. So I have ln q eta as minus eta sum over k ln 1 minus eta e to the power minus beta epsilon k minus mu. In the grand canonical ensemble, the different single particle states are occupied independently with the joint probability P of nk, which is given by 1 over q eta product over k e to the power beta minus beta epsilon k minus mu nk. So once you know this ln of q eta, I can calculate the thermodynamic quantities, and we start off with the average of the occupation number nk. Now when we did grand potential, we calculated average of n was del mu of ln q. I think there was a 1 by beta outside, but here one has to be careful because mu is tied to the total particle number. On the other hand, I want the average occupation number in the kth level. So what I do here is essentially I do minus del beta epsilon k, which does the same job of ln q eta, and this is given by then ln q eta is this, so this becomes plus eta. I am choosing only one value, specific value of k, so therefore I will pick up only one term in the sum and the kth term, which then becomes 1 minus eta e to the power minus beta epsilon k minus mu, and then you have eta minus eta e to the power minus beta epsilon k minus mu, so that your average occupation number is going to be, you are going to have a minus 1 from this derivative. It's going to be 1 over 1 minus eta e to the power minus beta epsilon k minus mu times e to the power minus beta epsilon k minus mu. So let's call z as e to the power beta mu. Then I can rewrite this expression as minus beta epsilon k e to the power beta mu, and here I have 1 minus beta epsilon k beta mu times eta, so that if I bring everything down, then this becomes z inverse e to the power beta epsilon k minus eta. So this is your average occupation number, which is z inverse e to the power beta epsilon k minus eta. This quantity z is known as the fugacity. Total particle number is given by sum over k average of nk, and therefore this becomes sum over k 1 over z inverse, which does not contain the k index, it's just e to the power beta mu, is e times beta epsilon k minus eta. What is the average energy? Is sum over epsilon k nk, which is going to be sum over epsilon k average of nk, which is z inverse e to the power beta epsilon k minus eta. The thermodynamic pressure, if you recall, beta p eta is ln of q eta divided by v, which is 1 by v sum over k so this is going to be minus eta over v sum over k ln of 1 minus eta e to the power minus beta epsilon k minus mu. Now in evaluating these sums, The idea is to convert them into an integral, and we have seen how to do this. So for example, then beta p eta is minus eta over v over 2 pi whole cube integral d cube of k ln 1 minus eta e to the power minus beta epsilon k minus mu. The particle number n is sum over nk. Sum over k is equal to v over twice pi whole cube integral d cube k 1 over z inverse e to the power beta epsilon k minus eta, and energy is sum over k epsilon k nk, which means this is going to be v over 2 pi whole cube integral d cube k epsilon k z inverse e to the power beta epsilon k minus eta. So to proceed further, let us just briefly summarize that what we have been doing. We have been looking at the ideal quantum gas from a grand canonical perspective, in which the particles in the energy state on the kth energy levels are allowed to vary, so you don't have a fixed number of particles. So your nk are different for different k levels, they can vary, but the condition is that sum over nk must be equal to the total particle number, and from this you calculate, using this you calculate the grand canonical partition function, and you relate it to the thermodynamic quantities that we have done over here. Since it's a free particle, since it's not, note that I have missed out the degeneracy factor, which is g over here. So for example, if you're looking at a fermionic system with each particle having a spin s, then this degeneracy factor is 2s plus 1. That needs to be accounted for. Good. So we will take these expressions and we will proceed further. So let's write down them as beta p eta is minus eta gv over 2 pi whole cube integral d cube k ln 1 minus eta z e to the power minus beta epsilon k. The total particle number, which is sum over k, this gets converted into g v twice pi whole cube integral d cube of k 1 minus z e to the power beta epsilon k minus eta, and the total energy is sum over k epsilon k average nk is gv twice pi whole cube integral d cube k epsilon k z e to the power beta epsilon k minus eta. Now we are looking at a free particle system on interacting, and therefore epsilon k is h square k square over twice m. So that we redefine our variable as x, and this implies x is beta h square k square over twice m, so that k is twice m beta h square half times x to the power half, and dk becomes twice m beta h bar square raised to the power half dx over x to the power half with the factor of half. Now if I look at this particular expression, it looks very familiar to me. Now I know that lambda t was beta h square over 2m pi raised to the power half. So then twice m over beta h bar square is nothing but twice m over beta h square times 4 pi square. So which means I can write this as 4 times 2m pi over 4 pi times 2m pi over beta h square, and therefore you see that this is 4 pi over lambda t square, so that twice m over beta h bar square raised to the power half is going to be 2 pi to the power half lambda t. Very nice. So then I have the relation that k is going to be 2 pi to the power half x to the power half divided by lambda t, and dk is going to be pi to the power half x to the power half over lambda t. So we are repeatedly going to use this as a measure. So starting from the expression for the pressure, which is minus, recall when I have this beta p eta, there was a 1 by v sitting over here, because beta p eta is essentially ln q eta over v. So the vv gets cancelled out, and therefore I will have minus eta g over twice pi whole cube, and then this measure becomes 4 pi k square dk. So I'm going to have 4 pi integral k square dk ln of 1 minus eta z e to the power minus x. Good. So let's simplify this further. Eta g, this becomes 8 pi cube, so you're going to have 2 pi square. K square is going to be 4 pi x over lambda t square. So you're going to have integral 4 pi x over lambda t square, and dk is going to be pi to the power half x to the power half. There is a dx missing over here. I'm terribly sorry for these silly mistakes. Dx ln 1 minus eta z e to the power minus x. This is minus eta g. You see, this factor gives you 2, and you have pi to the power 3 half and pi square in the denominator, so you get a square root pi straightforward, and then you get 1 over lambda t, the thermal de Broglie volume, and you have, so this means dk is going to be pi to the power half over lambda t dx over x to the power half. Now in the expression for beta p eta, there is a 1 by volume factor, so that the expression for beta p eta becomes minus eta g over 2 pi whole cube. The measure d cube k becomes k 4 pi k square dk, so the angular integral gives you 4 pi. I have 4 pi k square dk ln 1 minus z eta e to the power minus x. So that this is minus eta times g. This gives me 8 pi cube in the denominator and 4 pi in the numerator. That gives me 2 pi square, and the integral case, this I will change to now my transform variable in terms of x. This gives me 4 pi x over lambda t square. This is k square, and then dk is this which is going to be pi to the power half dx lambda t x to the power half ln 1 minus z eta e to the power minus x minus eta g 2 pi square. Now let's not do it over and over again. Let's just do a little bit of a mental math. So this is 4 in the numerator, 2 in the denominator. I straightforward have a 2 in the numerator. Numerator also has pi to the power 3 half and denominator has pi square, so I have a square root pi, and then this and this gives me the thermal de Broglie volume, so that I have dx, this and this gets me x to the power half ln 1 minus z eta e to the power minus x. So it's important that we rewrite this in terms of x, because we are going to repeatedly use it later on. Let's look at the energy. The energy is sum over k epsilon k average nk, which means this is going to be sum over k epsilon k z inverse e to the power beta epsilon k minus eta. And this, if I convert it to an integral, this is going to be gv over 2 pi whole cube integration k square dk. We will multiply this with beta, so that I have beta epsilon k throughout, and the reason is because I have defined beta epsilon k as x, so my life is going to be simpler. E to the power beta epsilon k minus eta. K square gv twice pi whole cube, sorry, there is a 4 pi also that comes from the measure, so this is straightforward. We don't want to do it over and over again. 2 pi square, k square is going to be 4 pi x over lambda t square, and dk is going to be pi to the power half dx over x to the power half and 1 over lambda t. And then I have x z inverse e to the power x minus eta, so this integral gives me twice gv over square root of pi 1 over lambda t integral dx. Now do a power counting in x. This is 1, this is 1, so x squared divided by x to the power half, so you get x to the power 3 half 1 over z inverse e to the power x minus eta. So this is beta e, and n is going to be sum over k nk, which is sum over k 1 over z inverse beta epsilon k minus eta, and therefore this is going to be gv over 2 pi square integral k square dk 1 over z inverse e to the power beta epsilon k minus eta. So that means this term is going to be gv over 2 pi square. I'm going to have 4 times pi to the power 3 half from k square and dk both, and this is going to be dx x to the power half z inverse e to the power beta, sorry, not beta x epsilon k, but just e to the power x minus eta. So that this again becomes twice gv, sorry, there is also going to be a thermal volume lambda t, don't forget that, 1 over lambda t dx x to the power half z inverse e to the power x minus eta. So these three expressions, this one, and finally this one, we are going to use later on. But right now let's focus on the pressure equation. The pressure equation tells you beta p eta is minus eta g twice eta g over square root pi 1 over lambda t dx x to the power half ln 1 minus eta z e to the power minus x. Good. Now x, recall, is e to the power beta epsilon k. So momentum can have 0 values to infinity. So k can be integrated from 0 to infinity, and therefore x also runs from 0 to infinity. And now I can integrate over parts so that the first term, I will take this as a first function. I have ln 1 minus eta z e to the power minus x, and the integral of x to the power half is x to the power 3 by 2 divided by 3 by 2, 0 to infinity, minus 0 to infinity d of x, x to the power 3 by 2, 3 by 2, derivative of this function with respect to x, which gives you eta z e to the power minus x. Then you have minus eta z e to the power minus x and a minus 1 because it's ddx of minus x. Close the bracket. Now, if x is equal to 0, ln 1 is 0. If x is equal to infinity, ln 1 is 0. So both the cases, this is 0. Okay, before we proceed further, let's just write down the limits so that we don't get confused later on. 0 to infinity. Come back to this. This is minus twice eta g over square root pi 1 over lambda t, and now I have a minus over here, I have a minus over here, that makes it a plus. I have a minus over here and a minus over here, that makes it a plus, so I have a plus. This term is 0. Further, note that I have a eta over here and a eta over here, that makes it eta square, and eta square is always 1 irrespective of whether you have a fermionic system or a bosonic system. So I can straightforward remove this, and I am going to have g. Then I am left out with two by 3 0 to infinity dx x to the power 3 half, eta I have taken care of, z inverse e to the power minus x times 1 minus eta z e to the power, z inverse e to the power plus x, and this. So this is going to be 2 by 3 2g over square root pi. I will multiply this by v, and I will bring down a factor 1 by v over here. You will see a little later y, and then this integral becomes dx x to the power 3 by 2 z inverse e to the power x minus eta. Now 2 by 3 this is 2 by 3 1 by v, and if you look at this expression that we have come to after using integration by parts, you will see that this is exactly this expression. There is a 1 by lambda t, 2gv square root pi 1 by lambda t 0 to infinity x to the power 3 half z inverse, and see, this is the same thing that we are looking at, and therefore you come up with the answer, this beta times e. So that p eta is 2 by 3 e over v. Therefore the pressure, irrespective of a fermionic gas or a bosonic gas, if it's a non-relativistic gas where epsilon k is h square k square over twice m, the pressure is 2/3 the energy density, something we derived in classical statistical mechanics, but we have done it now for quantum gases, quantum ideal gases.